Howdy, folks. Good day, good morning, good evening, wherever you are, whatever you're doing. Thanks for tuning into this. This is going to be a fairly lengthy topic. I put this material together over the past couple of weeks as I was searching around now that the S650 is open and able to be tuned. There's not a lot of material I found that sort of is a good A to Z. Here are the steps. Here's how you do it right. So based on some research, based on some screwing around, just a lot of experimenting with my own car, but staying safe. These are some of the key parameters I've discovered, and I think I have a pretty good method for tuning this that will be familiar to a lot of other tuners. In fact, they'll probably say, well, yeah, no, it's a no-brainer. But I think there's something in particular here, the high-low method that I'll explain, that I think will be valuable to a number of different folks. So without getting too far off the beaten path, let's start getting into the material here. Some background and things to consider as we do this. Unlike previous generations, but like the F-150, for example, Gen IV Coyote fuel trims are in fact speed density driven. Ask me how I know. I know because all the cars I've tuned in the past, first thing I've always started with is MAF. I drive mostly sport vehicles, sports cars, various stripes. I'm not really a truck tuner, so I'm used to MAFs and working with MAFs. And when I got into the S650 and started playing around with that process that I expected, I found that tuning the MAF was strange and peculiar. There's a way to do it, and I've explored that in other videos, and I'm going to get in more depth later on about it. But it turns out it's not what matters most. And I know that because I tuned my MAF. I got it within, I think, 2% across the board and thought, great, I've nailed it. I did it by isolating the MAF from speed density calculations. Once I turned speed density back on, hilarity ensued. The logs were just showing, oh, hey, you're back to like 5% lean across the board. And so this was sort of driving me crazy. Why is this happening? And I've seen in some of the HPTuners forums, and I think Mustang 7G as well, there are folks who will come through the room and cryptically say, the Mustangs this gen are speed density driven, and I didn't really believe it at first, but having seen the logs and having played around with this concept in particular, I'm now utterly convinced. Speed density trims are absolutely governed, or the fuel trims are absolutely governed by speed density, not mass airflow. Now that's not to say you're not going to want to tune both. You are still going to want to tune both. And I think actually I would still start with the MAF, and I would do it by isolating it, turn off all of the speed density calculations like cylinder air anticipation, things like that. Because you're still going to want to do that, but just know that when you're logging, you're going to see the SD is king, right? So in addition to that basic fact, I was surprised when I got into my Mustang to find that there are 4 oxygen sensors total. Many of you already know this, but I didn't coming to the platform. I had just been, prior to this, I was working pretty extensively on Chevy tuning and grappling with the virtual VE tables. And for the Camaro that I was doing as a project car, I had to go and get a wideband welded in. This is fully what I was expecting. And surprise, surprise again, the Mustang already has 2 pre-CAT wideband O2 sensors, which makes the tuning process easier, right? It's already there for you. In fact, I think there's a lot of the stuff that Ford has done for these engines that really favors the tuner. And this is one of those things. We've already got O2. In addition to that, though, thank you so much, Ford. On the Gen 4 intake manifold, there's the 2 throttle bodies up front. Looking forward to some twin turbo setups right down the line. On the rear, though, an unsung hero, there is a manifold pressure sensor. It's a real map sensor. It gets actual pressure readings. You can use those to just do all kinds of things, right? So we have both MAF and MAP. It's kind of the best of both worlds, which is pretty great. So other things to consider here. Speed density tuning, just as a refresher, unlike MAF, which I won't get into here, it's calculating volumetric efficiency, and it's doing it in a 3D chart against manifold pressure on one side and the crankshaft revolutions, RPM, on the other. And basically it says, I know from the geometry of the engine the volume of each of the respective cylinders. I know that I have air coming and going under load. I know that if I plot each of these points, right, I can have a lookup of a number that is essentially a percentage. For this load and for this RPM in this pocket, you're going to have a value of 0.58. which is going to be 58% of the total maximum air load possible, right? And so the engine says, okay, now I know what the mass air is going to be. Fantastic. And so with that, I also then know fuel, because I have fueling tables that'll match. When I came to this generation and tuning as of late, volumetric efficiency was a little new to me. I didn't have to play around with it as much in previous areas. Mazda Speeds in particular didn't really use these tables, but they did use three-dimensional fuel command tables, which you would then measure fuel trims against, right? And that's how you would correct your airflow model. This is something that I had to beat it into my head. It's not intuitive for me, and for others. VE tables are fueling tables, right? And I'll say it again. A VE table is a fueling table, right? It is a table where you're looking at conditions, and as a result of the calculations, we are commanding how much fuel to squirt into the engine, right, to match the air and get to the Stoich target that we're looking at, right? So that's what we're doing, right, is fuel calibration. Sometimes it's helpful to, as you get lost in the weeds of particular things, right, it's helpful. Why are we doing this? Because we're optimizing fueling calculations, right? So to do this, previous generations, if you wanted to do speed density tuning on a Mustang, what you had to do was go out and get you a Bosch sensor, a map sensor. 3 map is better, because what if you put on a supercharger down the line, right? Prep for forced induction. You would go and you would get this sensor, you would plumb it in to your intake manifold where you get a good vacuum reading, right? Or at least the pressure reading at any given moment. And then you have to figure out how to get that into your tuning software. HPTuners is what we're using here. And so you can either use the ProLink cable, which is the route I was going to go. In fact, I have an unopened ProLink cable sitting on my desk because I expected I was going to have to do this. But it so turns out that you really don't need to do it. And that's because, in addition to the fact they give you a map sensor, first of all, right? Normally we have to worry about open and closed loop transitions, especially if we didn't have a wideband to begin with, right? But the whole reason we put a wideband oxygen sensor in is so when we're in open loop and not using fuel trims, right, we are able to figure out what the commanded lambda was and then what we actually got, right? And that delta is what we use to correct our airflow model. Wouldn't you know it, in S650s, I've seen it in my logs time and time again. This ECU stays in closed loop during power enrichment and the optimal power VCT schedule, which means when you go watt, which is what we're really tuning for, right? We want to make sure that all these models are perfect. So when we start getting aggressive with our torque tables, our power enrichment tables, and our spark tables, we begin advancing timing, we have to know that our calibration is spot on, right? And they're so lucky with this gen that because this power mode stays closed loop, that means, guess what? I don't necessarily have to do the map exercise from the previous 3 generations. I can tune speed density across the whole VE table, because at any given moment, if I know pressure and I know RPM, I know where I am on the table, and I can look at my LTFT and STFT fuel trims, and I can, from those, see what percentage I'm off. I can go into my airflow model, and I can correct it, right? So if I was commanding 58% VE, and the result that came out was I got 55, right? I know I can drop it or adjust as I need it, right? See what I'm saying? This is a big deal. This streamlines the process considerably. There's a problem though. It's not all fun and games. If you're familiar with the platform, you know that the VE table, which normally would be one big 3D table, you would really dial in maybe over like 5, 8, dozen iterations even, right? The way that Ford has broken this up for the S650, like the S550 and previous even, is it's broken across these 28 smaller tables, and each one of these tables is mapped, right? Literally mapped points. There are 28 mapped points, and they are governed by a model that has a slope for the VE table. That's like the function, right? And then there's the offset. This is classic y equals mx plus b math. If you're not familiar, don't worry, we're not going to get into it. Just this is the parameter that's defining the mathematical model. And there's also the quadratic term itself, right? So the nuts and bolts of the math is tricky because you have to be able to adjust these three things, which is a huge pain in the ass, right? And Ford kind of deliberately did this, I think, so that, you know, not everybody can just walk in and start poking this car's brain. The good news, of course, most of you know, is that HPTuners has given us a speed density calculator that will translate these three tables into a classic volumetric efficiency table. We get our percentages, we come into this table, we adjust, right, and we post it to the file, and we're good to go. So that's one problem kind of solved. But there's another. The intake manifold runner control. And this is something that I mentioned in another video. You can check it out on my YouTube channel. I discuss more about what's going on here. But the bottom line is that whereas in previous generations we would absolutely just delete the IMRC, with the S650, because it's speed density driven and because this is how, you know, our everyday street driven airflow model, and because the IMRC gives us torque while we're down low, and I don't like sacrificing torque in any situation, I would rather keep my IMRC functioning. Now there's a lot of folks who will, hey, you're crazy, right? You don't need it. And that's true. For the, you know, I'm sure it can happen, right? But I want to have my cake and eat it too. I want to have the airflow that comes with the IMRC, but the problem is I have to take account for it, right? And we're going to get into later on how we deal with this. The other thing you have to understand if you're going to do this, and if you're not familiar with these, you're going to have to put the time in and do the studying. But the variable cam timing schedules, how they work, what they are, how the driving modes work that are governed by the high degree of freedom execution model, or HDFX, and how it moves through those. Understanding it's all load-based, and we'll show you more what I mean by that. But you've got to understand all that if you're going to follow this process. If you do, though, you can completely tune all your fuel trims across the 28 VE tables, and that's it. You've got it dialed in. Add that to your math, and you're good to go. And so, you know, later on, if you add headers and your flow changes, it's as simple as mapping your deltas, putting them through the tables, and off you go. So how do we do this? So the high-low method, which is what I devised to do this for myself, because I want to keep the IMRC for the reasons I explained, right? I don't want to give up low-end torque. But I don't want to tune 28 VE tables. My God, right? Like, it's just too much. So others may have discovered this, but I discovered it on my own. And basically it's this, and I describe it in the IMRC video as well. We take advantage of how the HDFX moves between the intake manifold runner control states, which are high and low, right? There is a load point in the file for the IMRC, and if it's under that load point, it closes it, and if it's above it, it opens it, right? And it's got a corresponding voltage. The way the tables work is the bottom three tables, and this is where I'm going to start switching over to a file here, because it's going to make more sense. Here are the IMRCs, and you can see we have a number of them. 0 through 9 is when the IMRC is open, and 10 through 19 is when the IMRC is closed. And unlike other generations, the S650 has a new set of tables up top here, a new configuration where there's these other like 7 tables up top. Those are in fact power tables. And if we put this off to the side here, and we come to our camshaft, if we go ahead and open our intake valve and our exhaust valve mapping, where'd my exhaust valve go? He runs away on me sometimes. There we go. There it is. Okay. Things get foobar on me. If you look at these tables, you will notice, like previous gens, 0 through 9 is a replica of what's in 10 through 19. And the reason for that is because 0 through 10 and, 0 through 9 and 10 through 19, they're essentially the same table. I go into this in the other video. One's high, one's low. So, and the way they work is if you look at the load definition point, we'll take just fuel economy, right? Where low load is closed, high load is open. We have a little threshold here, right? And we can see in the different loading positions what needs to happen to switch from the voltage from one to the other. Now, let's get into some practicals, right? When you look at logs, and this is how I've constructed mine, right? If you look at it, you will see down here where you're mapping your points, you will see that it moves through. Table 1 is active when the voltage is low, like I was showing you. And then if voltage goes high, let's see, there we go, table 1 becomes active. Okay, so this is the point last night where I had some audio issues, and so we're going to step through this again with the magic of editing. As you can see in this particular log that I'm working on, once again, for the most part, when I'm in a low load state and my voltage here for the IMRC is low, my table 13 is active. If I move through the table and reach a power situation though, and this will flicker, you can see how it flickers, the nature of it, right? But every once in a while, if the runner turns on, I'm at 0.3, the 0.3 activates, right? So this is the feature that lets us zero in on how we're going to capture both of these tables at once, and that's the goal. And so let me take a minute on that as well as the LTFTs. So I leave my LTFTs on. I've noticed that the ECU is more than capable of calculating that, and that the percentages I get in aggregate I'm able to apply to my tables, and I'm getting fairly good results. If you are not seeing results, the old school tuning method and the right way, in quotes, is you could turn your LTFTs off and govern just against your STFTs and use those to dial in. That would work as well. The whole guiding ethos behind this, though, is we want to touch as minimum as possible and make a path that is as efficient as possible, right? And that correlates to driving states in the real world, right? And that's the whole point here. So, having them on, great. If you were to turn them off, it's just an extra step in the process, right? So just wanted to comment. The other thing I was going to mention, while you're taking your logs, it's very important with this process that we get accurate data and enough data, and that it's across all of the different situations that the vehicle's going to be in. So like with any speed density log, when you're doing math, you can just do a couple of rips down the road, 10 minutes, go and adjust, you can bang it out in an afternoon. It's no big deal. With speed density, because you have to hit all these various pockets, it's going to have to be a pretty long drive, right? And I've actually gotten this down to, for the most part, a 3-step process. And so the first log that I do tends to be a getting to know you log. It's only about 20 to 30 minutes driving around, and you need to hit all of the different various conditions that you would hit in normal driving. And so things like hills, things like accelerating, right, hitting your RPM ranges by uncorking it in second gear on a country road. You start at about 25 miles an hour, you get it up to like 60, 70, all in second gear. That's going to move through the power band in various different states. And then as you press the pedal down, right, you can floor it, and that's going to get you your, high power, high load situations. And it's going to, get a lot of pressure. If you are stabbing it though and coming in a little lower, right, it'll still move through the power band, but with slightly less pressure readings, right? This varied approach, and I'd say the other part of it is that's your high RPM. Another thing in the same run I will tend to do is pick up the interstate, right? And so you're cruising at 65, fifth and sixth gear, between 2,000 and 2,500 RPM when you start, and you can get that low pressure, low load data, right, where you're barely touching the throttle, and that helps you map like 1400, 1500, etc. Where we really want to target those like 1600 and above. And you also want to get high pressure situations at those low RPMs. And the interstate's perfect for that because you can be in sixth gear and absolutely floor it in this state, right? And the other thing I'll say is, as you isolate these mapped points, you are locking the crankshafts in for these ones, right? An economy position, essentially, right? We're not moving to like the positions that make massive power. So it's great because you'll be out on the interstate and you can like get it into 70, 80, 90% throttle. You're jamming, you're just mashing your pedal, and the car doesn't do much. It kind of feels like a wet sponge, which is nice because that helps you get that high pressure data that you're looking for, right? So these are some of the techniques. And when you look at the logs, you start to get this lovely map. And so a couple of things here. You can see my long-term fuel trims across the board in this iteration. Little lean, nothing major. They're joined by the ST fuel trims, and we're seeing as well they're pretty much within range. I'm not seeing wild, big, crazy corrections. That's what I want to see. I'm also noticing that I'm doing my MAF calibration, right? And this is how I originally set up the MAF when I isolated just the MAF, turned off the speed density calcs. But with the whole thing operating, you'll see that these will map the lean state. And it's tempting to say, oh, I could just tune to this. Nope. You come over here to low, and this is the real distribution of airflow model error across the pressure and RPM. You can see we're coming in pretty lean. It's a pretty good sampling of data. This was a 43-minute log, pretty good, and you see we're hitting some pretty great data points. Obviously in here is my really accurate pocket. I would even say, in here is hyper accurate. I can take that to the bank. This is definitely just a little lean, right? And that's what I would expect to see given that we're stock, and this is what Ford gave us, right? It's no big deal. And this has gone through one iteration of tuning already. When I started, it was probably like 5%, 6% lean. But these counts are pretty good. And the way that I'm setting up this graph, just to show you the method, LTFT plus STFT, banks separated, got them. 2 decimals. I'm filtering on the low state of the IMRC voltage, which happens to be about 1.5 volts, I've noticed. So to keep it safe and to really isolate the low condition, I don't want to see the flicker states, if you will. I keep this under 2 volts, and I also come over here and I select my mapped point 13. So this is the low load condition. I only need to worry about setting it up for map point 13. I don't need to worry about setting it up for map point 3. I don't need to worry about doubling back and grabbing map point 3. By mapping map point 13, this is the magic of the high-low method, map point 3 is going to come along for the ride. How does this happen, you say? Because we have our high voltage state as well. Still looking at IMRC. but this time we're looking for loads above 3 volts. The high state is about 3.2, 3.3 volts. Again, we want to ignore that transient range. We can set it here to 3 volts. That'll get us those buckets. And as well, we can look at mapped point 3. Only log when map point 3 is active. And we set this cell hits at about 5. Because we're getting less hits in this state, 5 is usually pretty good to give you the trending without bringing along noise. For the low condition, 10 is usually pretty good. And you can adjust these a little bit. Again, this is where the art takes over the science. So for example, if we start looking this, if I have 0, right, there's some noise that comes along for the ride. Let's just take a look just for a sec. I don't want these. These are crap, right? It doesn't mean anything. That, who knows what the hell was going on there, right? It's not real data. Likewise over here, real high in the pressure zone. Yeah, it's not great. The count looks pretty good. But now if I go back and I say something like 25, those are hyper accurate. You could start there, no big deal. But you're shaving off quite a lot of data. If I was to do something like 5, I could have probably done that, right? 10 though, I think, is accurate, gives me the trending I want, looks good, right? And so likewise, that's the low state. If I go to high here, same song and dance, you're looking for trending, right? And so here, I like this because, first of all, I'm not too far off, which is good news. This 4.3, that only happened 5 times, but yeah, I'll take it, right? This gives me a good picture of what was happening in the high state. And this is the other kind of thing about this. These two tables together, you can see how they complement each other, right? It's one part of the range versus the other. If I was to have both of these in one table, that's a pretty good speed density VE adjustment, So, this is the shape you should be seeing. And the great thing about this is, you maybe ask yourself, well, what about these values down here for map point 3? It doesn't matter. It doesn't matter because map point 3 will give way to map point 13 when we're at these lower load situations, right? That's the beauty of them. And so you don't need to map all 20. You can map the 10, right? That's the trick here. And so how to actually use it is pretty simple. I would be in my tune. I would come over to my speed density calculator. We'll blow that up. And I would start with table 3 here in the tune. And here's my VE table. Looks clean and happy. I come over to my data. We copy. Come back to my tune. Paste special. And with these subtle adjustments, I have found multiplying by half is good as well, given that we have LTFT operating still. Multiplying by percent you can do. It's a pretty heavy swing in one direction. I've noticed that if you do this, you might be coming in about 7 degrees lean. You do a huge adjustment. Now you're coming in 3 degrees rich, right? That's where you definitely want to come to multiply by half. So we do that, and voila. Couple of pro tips here. One, when you hit this button, there's no going back. And so what if something weird happens? And by weird, I mean, what if I see goofy, shitty noise that looks like this, right? If you're seeing these after these adjustments, excluding this bizarre monster here, which makes me freak out, but that is what came stock. But otherwise, if you're seeing spikes and valleys like that, something's wrong, and it's going to make your tables look goofy. And if you hit calculate coefficients, you can't go back. So let me back those out. Now I back the whole thing out. That's fine. Before I apply the changes, I do one last copy. Because then if I come in and do calculate, if something goofy happened and I didn't like it, I don't care. I can just go back to that state before I applied it, right? And I can smooth and move things, that's fine. And that experience comes from the Chevy VVE tables, which are an absolute bear. I have found this guy really, if you're doing this method with small adjustments, I've yet to see it make peculiar shapes. Now I say that, you may be pulling your hair out saying, fuck you, this thing's terrible. I'm just saying, so far for me, this has proven fairly reliable, right? So let me know if your mileage varies. Having done map point 3, I now come to map point 13, the low state, now that I've done the high state. And so I go to my low table that's filtering on low IMRC voltage. I grab that, I copy it, I come on over to the software, map point 13, double check. I do the old pasty. I say, yep, that looks good. That's what I want to do. Bang. And that's it. You save it to your file, and you are good to go. And that, well, now you can let rip, and you would come over and you would do the next set of your logs, right? So, pretty easy, pretty good. I've gone through half of my speed density tables at this point and done all this. Once that is all complete, then you will see your trims have pretty much lined up, and you can think about the optimum power tables. So let's go back to the tune for a second, talk about that. Optimum power is interesting because ultimately what you would do is go back to your stock values for these guys and leave them handy. And that is when we can also then begin thinking about mapped points 20 through 26. And if we look at the speed density calculator, we can come here to map point 20. Let me give you a word actually on this. Maps 10 and 11 I refer to as my stable tables, right? 0 and 11, the system likes to live in these states. Let's go ahead and yep. You will see in your logs you spend a lot of time at map point 10 and map point 11. It's almost like a 50% breakdown. So it behooves you to really spend some time, make multiple passes, really dial this in. Because if you are out cruising around and you're hitting partial throttle or full throttle and suddenly demanding a lot of power, the airflow model for these tables is absolutely vital, right, to get right. The other ones, you're going to want to tune them, right, but it doesn't spend as much time as it does 10 and 11. And by, inferring with the high-low method, also it spends a lot of time in 0 and 1. Optimal power, likewise, relies on table 20 quite a bit. Damn thing did it to me again. So, finishing my thought, optimum power, map point 20, we'll definitely want to spend a lot of time there. And the way we would do this, just to say, is we would still go to our tables. We would still, for example, isolate the table. The way I do it is, you can put map point 20, and just like you get your values here, right? Map point 20, -40. I would come over here to my intake, and I would set it -40, right? And that's a hell of an advancement, right? So there's a reason it makes power there. That's when I would it's different, just like MAF tuning is done in a two-step process where you do the low end, right? When that's all dialed in, you go and worry about your watt MAF tuning. Same thing here. The speed density tuning for these tables, states 20 through 26, this is high power. This is near watt or watt itself. This is big partial throttle acceleration. And so we don't need to drive around town as much. This is where we would just do a couple of watt pulls. And if everything's looking good, right, circle in on it like before, adding 0.5%. And then you've got your high end done. I worry less about 21 through 25 simply because when you look at the logs and how this blends it together, it doesn't spend a lot of time in those, and when it does, the percentages are quite low. In fact, I think it would probably be pretty challenging to try and tune those. Once I'm done with most of my speed density tables, I'm going to perform the process, and we'll give feedback. In fact, I might have a quick little, much shorter 5-10 minute video on just the optimum power watt specifics of the method and how this all works, right? So why are we doing this? So again, the whole reason this started is this is the most fundamental fuel trim operation you need to perform. It's step one in an order of operations. And it's peculiar because normally you would go MAF, then speed density, right? Then worry about torque, fuel blending, spark, right? For this, it's not quite like an F-150 where we just do speed density and that's it, right? The process I follow is I do my MAF first. And part of that is because I know that when I'm out doing the speed density, right, and if I have my LTFT and STFT ons, and while I'm doing speed density, I have redundant overlapping MAF sensors, and it makes me feel very safe. Again, the pedal feels squishy. I can be doing watt pulls. I know that everything's in order, and in my logs, I'm not seeing knock. I'm not seeing, issues, right? The engine feels like it's perfectly safe. I don't feel like I'm putting anything at risk, which is a big deal because Gen 4s just dropped. I mean, I've only had my car for 3 months now, right? But I feel very comfortable using this method. So then, so having done the MAF, right, then we go ahead and do all the speed density tables using the pressure sensors, and then we'll put those all together with the blended math and rip a couple logs, and you should see that the fuel trims against the pressure points and the fuel trims against the airflow points should all be in line. I like to shoot within 2%. Within 5 is more than acceptable, but I really like to get it locked in because, of course, once you get into the world of power enrichment, let's have fun and look at that. This is where we want to start having fun with this little table. This is the devil's table, right? Right? When you have everything dialed in and you have a good source of 93, God forbid we actually switch over to E85, that's a whole other thing. But when you are running on good, clean fuel and everything's tight and tidy, you can up these. And, I can lean these out to something like 0.84, maybe even 0.85. That's pretty ballsy, right? But these little guys in here, right, you can make a little leaner, which is going to command a little more power, and the cylinders will stay cool because you've got good fuel and everything's dialed in. And this is where the little extra bit of juice comes, right? Especially for guys like me who are tuning on the street. We are not going to worry about spark timing as much because to really play with spark, you need a dyno. I don't have access to one because I'm just a guy who likes tuning. I'm not a professional tuner. I don't have a shop with a dyno in it. That would be nice, but that's not where we're at, right? I'm just a guy having fun with my car, right? And if you are too, hope you're getting a lot out of this. I will end by saying this was a kind of an advanced topic meant for other tuners. Down the road, I really want to make a series of slides and tutorials that are for someone who is new to tuning, who happens to be tuning on a Mustang as their first project. That'll be coming, but this for now is where we're at. So I thank you, and like and subscribe if you got something out of this, and take it light. Stay safe out there. Have a good one.